So in this video I'm going to talk about stationary points, what do they look like, how do we define them, and I'm going to go through an example. So I've started off, I've drawn four functions here. Each of them has what we call a stationary point. Now we define a stationary point when the slope of the function is equal to 0. So let's write that down. Slope is equal to 0. Or, if we want to get a bit more specific when we're talking about derivatives, our first derivative, f-x, is equal to 0. So the slope is equal to 0. So you can see that there'd be a point there, somewhere there, somewhere in probably around about here, and somewhere about here. So each of these four functions has what we call a stationary point. Well, if we want to get really specific, these two are stationary points, these two here are stationary inflections. So I'll write that in there. Stationary inflections. So what are these going to look like when we draw a sine diagram of our derivative function? For one like this here, it's going to look a little bit like this. We're going to have some value, let's just call it x. And this side is going to be positive, and this side is going to be negative. And we have a specific name for this one, and we call this a local maximum. What about this one here? Let's look at the sine diagram for this one. So if this is a local maximum and the sine diagram looks like this, it's reasonable to assume that the sine diagram of this one is going to be the opposite. So we're going to have, again, some arbitrary value, we'll call it x, line through, and it's going to be negative to positive. So the slope here is negative, the slope here is positive, the slope here is positive, the slope here is negative, and we call this one the opposite of local maximum. Well, local still stays the same, but it's a minimum. So that's our two stationary points. What about stationary inflections? Well, first of all, let's draw the sine diagram of this first one here. And this one is going to look a little bit like this. Again, some arbitrary value of x. And we can see that the slope here is positive and the slope here is also positive. So our sine diagram is going to look like that. And this one here, again, we've got a line, some arbitrary point x, and we can see that the slope here is negative and the slope here is also negative. So our sine diagram is going to look like that. We don't have a name for the different types of inflections, they're just both stationary inflections, hence why I've left the name like that. So we could also call these here, these local minimum and maximum, we could also call them turning points. So why don't we go and have a look at an example, and see how this all will work out. So I've grabbed this example from the textbook. In fact, it is exercise 3C, question 1. And we've got a graph of f of x is equal to minus x to the power 3 plus 3x squared plus 9x minus 7. And it looks something like this. The first part of the question asks us to clarify the stationary points A and B. So if we have a look, I've got a point here A and a point here B. What's the name that we give to this one? Well, if we go back and have a look at what our definition is, A looks a little bit like this, where it's a local minimum. So we could say, let's go A, that point A is a local minimum, and that point B is a local, in this case it's looking like that, local maximum. So that's the answer to part A. What about part B? So we've got to find f dash x and draw its sign diagram. So first of all, f dash x is just asking us to find its derivative. So in this case we've got minus 3x squared. We should really start off with f dash x is equal to minus 3x squared plus 6x plus 9. Now we can factorize this and take out a common factor of minus 3. So let's do that. So we've got minus 3 out the front, x squared, take 2x, take 3. Now the reason we're changing the signs here is because we're multiplying it by a negative number. We've got to multiply it by a negative number in order to get a positive. We can still further factorize this and put it into brackets. So our final answer for here, well, our final answer for our derivative is going to be x plus 1 x minus 3. Now, the way I've done it is thought of what two numbers, when multiplied together, create minus 3, but when added together, create minus 2. So minus 3 plus 1 is minus 2, minus 3 plus 1 is equal to minus 3. So we know that there's going to be, to make this entire function equal to 0, because remember with our definition that these points occur when our slope is equal to 0. To make this entire function 0, or equal to 0, there are two values of x that we can have. And they are, so f dash x is equal to 0 when x is equal to either minus 1, because minus 1 plus 1 equals 0, or 3. 3 take 3 is also 0. So now we can draw our sign diagram. So we know that we're going to now have, I'm going to draw it along there, a point here at -1 and a point somewhere here at 3. I don't mind if these aren't quite to scale, as long as you can see where -1 and 3 are. So we've got to try and work out what is the function doing at before A, between A and B, and after B. So A occurs when x is equal to -1, B occurs when x is equal to 3. We have a look, everything this side of our y-axis is x when x is equal to negative, everything over this side is when x is positive. So let's plug in a value into this function here of, say, let's go -2, and let's see what it comes out to be. So when we have f of -2, it's going to equal -3 -2 plus 1 -2 take 3. And this is going to be equal to what? So we've got -3 times -2 times 2 take 3 is -5. So let's see, we've got -3 times -2, which is -6, times -5 is going to be equal to -30. So over this side, it's going to be negative. Let's pick a point, say, when x is equal to, let's pick 0. It's a point between A and B. F of 0, so it's going to be equal to -3. 0 plus 1. Zero, take 3. Alright, let's have a look. Got 0 times 1, 3 times 1, -3 times 1, which is -3, times -3 is going to be 9. So it's got to be positive in here. And let's see what happens after B. We'll go, why don't we see for when x is equal to 4. So we're going to have -3, 4 plus 1, 4 take 3. So -3 times 5 times 1. -3 times 5 is -15, times 1 is still -15. So over this side, our function, or the slope of our function, is negative. So that's our sine diagram for part B. Now we've got to find the coordinates of A and B. Well, we already know that we've got two values of x here, so x is -1 and x is 3 for our slope. So we know that these are x coordinates of A and B. Now we've just got to find the y coordinates. So what we do, we just plug these numbers, these -1 and 3, back into our original function and see what the value is. So let's have a look. We've got, and I'm going to scroll down a little bit, rewrite the function out so we can actually see it. So f of x is equal to minus x cubed plus 3x squared x squared plus 9x take 7. Alright, now I've got that, we can move on. Alright, so let's start off with minus 1 and see what f is equal to. So f of minus 1 is going to be equal to minus 1 to the power of 3 plus 3 times minus 1 squared plus 9 times minus 1 takes 7. Alright, minus 1 times minus 1 is plus 1, times minus 1 is negative 1. Negative is going to make it a positive 1, plus minus 1 times minus 1 is positive 1. Positive 1 times 3 is 3. Plus 9 times minus 1 is just minus 9. Take 7. And let's work it out. So 1 plus 3 is 4. Take 9 is minus 5. Take 7 is minus 13. So we know that point A has the coordinates of minus 1, minus 13. Alright, let's look at point B, where x is equal to 3. So f of 3 is equal to minus 3 squared plus 3 squared plus 9 times 3 takes 7. Alright, 3 times 3 is 9, times 3 is 27, so we've got minus 27. 3 times 3 is 9, times 3 is plus 27, plus 9 times 3 is 27, take 7. So we've got 27 minus 27 plus 27, which is just equal to 0. So we've got this being equal to 0. 27 minus 7 is just 20. So we know that the coordinates for point B are going to be 3, 20. Now, if we wanted to check this graphically, we could put this in our graphics calculator and then see if when x is equal to 1, calculate the value of y, and when x is equal to 3, calculate the value of y. We could do that in our graphics calculators to make sure that we have indeed got it right, but the maths here is pretty sound, and I've double checked it and it's all right. So in a test situation or your exam, when you get to a point like this, or if you get a question like this, get your function, plug in the value of minus 1, or plug in your function minus x cubed plus 3x squared plus 9x minus 7, graph it, and find what y is equal to when x is equal to 1. Also find what y is equal to when x is equal to 3, or whatever it's asking you to do, to make sure that you get this bit of the maths right, because that's easy marks in a test. Alright, hopefully that makes sense with stationary points. Next I'm going to talk about inflection and shape, where we start to use the second derivative. hopefully it makes sense. If you've got any questions, please ask, and as always, thanks for watching.